Okay. Binary equivalent of negative 482. So what'd you first have to do? You had to, well, you were encoding this in 2's complement, right?
Yeah.
So negative 482 is going to require you to encode it in 2's complement. So you do 482, flip all the bits, and add 1. That's the 2's complement version of negative 482.
Yep.
Good. All right, next one. What is the hexadecimal equivalent of the octal number? Blah, 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 blah. Okay, this one actually would have been pretty easy because you have this octal number. Anybody use the trick, the shortcut? Shortcut? What shortcut? Yeah, so there's a long way where you can convert that to decimal and then convert it back to hex.
That's what I did.
Yeah, well, so you didn't use a shortcut. Why is octal popular?
Because you make it popular, that's why.
No, there's a much better answer to that.
It is a power of 2.
It's a power of 2. So what are the legal values in the octal language?
1 to 7. 0 to 7.
0 to 7. So 0 to 7 can be represented as 3 bits. So we're going to have a 3-bit representation of a 2. 3-bit representation of a 2 is 0, 1, 0. 3-bit representation of a 5 is 1, 0, 1. 3-bit representation of a 6 is 1, 1, 0. 3-bit representation of a 2 is 0, 1, 0. 3-bit representation of a 7 is 1, 1, 1. 3-bit representation of a 4 is 1, 0, 0. 3-bit representation of a 3 is 0, 1, 1. Okay? Then you put all those together, so that's 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1. Then you go through and you separate them into groups of 4, because that's how hexadecimal can be represented.
You get one group of 3 up there.
Oh, this one, thank you. Like that. So this guy is what value? This is 1s, 2s, 4s, 8s. So this is 8 plus 2. This is 10. So that's an A. This is 14. What's 14? E. 0, 1, so 1s, 2s, 4s. So this is a 5. 5. This is another E. And this is a 3. That guy?
Where's the shortcut part?
That's the shortcut.
Oh, okay. You don't get it?
Well, it's shorter than.
Yeah.
What do you mean that's not a shortcut?
I thought that was the long way.
Yeah, I thought that was a long way.
That's easier than dividing.
That is way, way, way easier than taking this octal number, turning it into decimal, and then taking that decimal number and converting it back to hex.
It is.
I don't remember. I thought I did it like that. But you
I was trying to split that number up into 3s, and I was tripping me up. And rather than taking each individual digit.
Yeah, this is the reason why octal is popular. You can represent all the octal values in exactly 3 bits. You can represent all the hexadecimal values in exactly 4 bits. At some point, once our values get larger and larger and larger, you can represent all of the 32-bit values in 5 bits, so on and so forth. Make sense? You can represent all the 4-bit values in 2 bits. So technically a base 4 would have this trick associated with it as well. All right, so that one would have been easy if you gathered saw the trick. What's the difference between a load and a store command? Store, when would you use each of these in assembly program? So load takes something from hard drive, puts it into a register. Store takes something from a register, puts it on the hard drive, puts it into data memory. Yep. All right, that makes sense. The difference between them? Well, when would you use a load? Well, when you needed to do some math on something, you needed to perform some operation on a value, you would bring it from data memory into a register so you could operate on it. Because in order for us to do any sort of stuff, we need to operate on it. When might we use a store? Well, if we want to, huh?
When you're done.
Yeah, when you're done, or you need to free up that register to use that register for something else, but you don't want to lose the value, something like that. All right, write a MIPS assembly code to sum all the numbers between whatever's in T0 and whatever is in T1. I said you can assume that they're already preloaded. Store all the results in T3. You should include the value in T0 and T1 in your sum. So, kind of like the loop thing we did for homework, where you go through and you just keep jumping back up until you finally finish your count, summing everything up inside of one register. And where did I say to put it? In T3? Put it in T3 at the end. All right. Explain in detail how input and output are accomplished in MIPS assembly. So input, well, both of them have you loading stuff into a certain register, which triggers it to go into input or output mode, right? And then it either dumps out from a register or says it's time to read in, and it reads in and putting the result into a register. What is the difference between a line of code in Java, an assembly instruction, and a machine code instruction? Well, so a line of code in Java is a high-level instruction, right? High-level code has a one-to-many relationship with low-level code or with a CPU. So that means one line of code in Java would get translated into, let's say, a whole bunch of lines of MIPS code, right? An assembly instruction. So an assembly instruction would be like a MIPS instruction. So we're loading something or we're storing something. So it looks English-like, but it has a one-to-one relationship with the CPU. What's machine code? Zeros and ones. Make sense? If you remember, I think one of the last parts of the MIPS section, actually it was the compiler section, was viewing how MIPS code is represented in machine code. Showed you it's like 5-bit banks for the different things. What does a compiler ultimately do?
Go back.
Who?
Why do they need to be different?
Oh, sorry. Why do they need to be different? Human beings like using power tools, so we like high-level languages where we write one line of code and it translates into a whole bunch of magic tricks on the CPU. Assembly code is still human writable, but it allows us to work with the CPU at a very, very, very granular level if we wanted to. But we like relying on a compiler to translate our high-level code into that low-level code. And ultimately, machine code is what the CPU actually eats, because CPUs like zeros and ones. They work with numbers. All right, so we need to have the thing that the computer understands and likes. We have to have the thing that the human being likes, and then we have to have the thing in the middle that the human being can tolerate if they had to. So we translate from the high level to the low level, which then gets assembled into linked into the machine code. So that's why these guys are different than each other.
I have a hard time understanding that question. Just I read it as why do these three codes need to be different? I'm like, well, I didn't write this. Like, why was as far as I don't know, how do I explain? The way that you phrased that sounded like I needed to explain why Java and assembly and machine code need to be different from each other.
Okay, so what would you say?
I didn't give an answer because I didn't understand because I didn't think there was an answer. I think that like the answer that you gave would be, why do we use Java versus write machine code?
Well,
The way that I would rephrase it.
Well, that's what a human. So I'm asking, we treat these as three separate products. If Java is one product and machine code is another product and assembly instructions are another product, why do these guys need to be different? Well, their audiences are different. The audience for Java code is a human being. The audience for machine code is a computer. The audience for assembly code is, let's call it, a subset of human beings. People that need to be operating at that very, very granular level. We make very small changes to code. I think when we talked about assembly, we said something along the lines of, like, if you're like a video game, majority of the video game might be written in a high level language, but let's say there's one part in the game that just needs to be super, super, super fast. You might go in and tweak that part of the compiled code in assembly to make to maybe remove any questions, conditions that you know just would never happen. So sometimes a high level language makes you put something in an if statement or makes you return a value or something like that, giving you some extraneous instructions. But maybe as the human being, you say, I happen to know this case will never happen. Or if it does happen, other bad things have occurred and my computer might as well just crash. Crashing is no better off than what will happen otherwise, something like that. So there is a reason why a human being might need to operate with assembly, but just like any other product, these are different audiences, I guess. So, I think there's probably several correct answers to that question. I meant it in maybe a certain way, but I think there's plenty of maybe reasonable, but not answering is probably not the greatest solution, I'm thinking.
Okay.
But
I just was confused by the way you phrased it.
let's see. What does the compiler ultimately do? Converts from a high-level language like Java into a low-level language like MIPS, or in Java's case, Java bytecode. What differentiates a good compiler from a bad one? Well, how well it or how efficiently it converts your high-level code into efficient low-level code, fast-running low-level code. So a compiler is accurate if it turns your high-level code into functionally equivalent low-level code. Now, a better compiler would turn it into optimized, functionally equivalent low-level code. That's what makes one compiler better than another.
I have another question.
Yep.
I think a good compiler also has to be able to say it's a fully maximize the architecture.
Okay, isn't that kind of covered in optimized? But I see what you're saying. That if a certain architecture that you're targeting with a compiler, if that has a certain special feature, it should take advantage of any little shortcuts, special features type things that the architecture supports to make the code even more optimized.
Yeah.
So the more optimized while still being correct the code is, the better the compiler.
And another thing is, say, supposedly is one CPU has 128 register, another CPU has 256. Doesn't always mean that using all this one will be always generating a better compiled.
Right, but that's usually driven by the. The number of registers doesn't say anything about how optimized the assembly code would be. You just have a little more runway with how much you can get away with poor register management, let's say. But sometimes you have like a server version of a chip versus a consumer version of a processor. Usually, in fact, I don't know if I can come up with an example where the same architecture chip had a different number of registers. Usually, number of registers is a set thing for a type of architecture. What changes is like the amount of various caches. So like L1, L2, L3 cache tend to go way up, which allows you to have things staged in closer, faster memory than data memory. Data memory is usually a synonym for saying RAM, your system memory in your computer. So like the data memory in this is my 32 gigs of RAM. Well, what might sit between that and my actual registers is L1, L2, and L3 cache. So much smaller, but really, really fast memory. So if I can get things partially stored in one of those closer things, then I can get it onto the CPU quicker. Because loading from data memory into a register takes more time than loading from L1 cache into a register, for example. So a lot of times server processors have more L1, L2, and then L3 cache is shared between multiple CPUs.
One more thing on this question. On my answer, I said something about efficiency, of course, but I also put something that best compiler will also depends on your needs. More in a commercial way, for example, you can have an open source compiler, which is better for you because it's cheaper, but it can not be compatible with what your clients use, so might not be, you know what I mean? Could be like a good compiler for one situation, but not for others. So compilers, they also depend on your needs.
Okay. So, but how would needs change for a company that would dictate one compiler is better than another? What's the need that changes?
Well, if you just have Microsoft technology, so an open source compiler will not be the best option for you or for your company.
Oh, okay. So you're talking more, so a compiler always takes a high-level language, converts it to a low-level language. So the idea would be if you are a Microsoft shop, your high-level language would be like C#, right? So right off the bat, the compiler you're going to be forced to use is going to be Microsoft provided or a mono project C# compiler. If you're doing anything with .NET, you're probably going to be married to a Microsoft-based compiler regardless. So that doesn't make the Microsoft compiler a better compiler than the Java compiler. It just makes it the correct compiler. It's the correct tool for the job. Yeah, so
The best for your needs.
yeah. So I mean that's. I would say if that's the only thing you said, it's probably not a great answer. But I mean, the optimization thing is the real important thing there. But I mean, at the end of the day, it's kind of what you're talking about is like use the right tool for the job. So you would not use a .NET compiler for Java because it won't work, right? So that's a bad compiler for that choice. But ultimately, the result of a compiler is low-level code, and compilers can then be measured in terms of the optimization of the low-level code for the target architecture, where a Java compiler would do a very, very, very poor job of creating low-level code for .NET, right? So it would certainly be a weaker compiler than the C# compiler from .NET. So it would be the wrong tool for the job because it doesn't understand the source language. We wrote our compiler in here to support kind of a very, very tiny version of C, right? That was our source high-level language, and then our target low-level language was MIPS. So we converted from C into MIPS, but we did it in an unoptimized way. Somebody else's compiler that went from C to MIPS would be better than ours if they had optimized output from that. Give an example of what a good compiler allows us to do. So what can we accomplish with good compilers? Faster stuff, right? It allows us to, a couple different things. It allows us to write things more like video games, stuff like that rely on performance. It also allows us to spend less time tweaking low-level code. For most developers, we don't spend very much time, if ever, going in and actually tweaking low-level code. But if we can trust that our compiler is producing optimized stuff, well, then we don't have to spend a lot of time going in and tweaking it, right? But then it also allows us to solve more complex problems without worrying about the efficiency of the underlying code, especially big mathy, scientific-y type problems can become unwieldy if we're converting it into very, very low-level things. If you look at our compiler we wrote, we would start running out of registers, right? If we stored too many things, whereas a better compiler might allow somebody to create 10,000 variables and be able to manage that with data memory and things like that, where ours would not have. What is the range of values that could fit into a 64-bit signed number? So we're talking about the difference between signed and unsigned numbers. So a 64-bit, so range of values that fit into a 64-bit signed integer That's 2 to the 63rd power. So it's that. You could probably write it as this. 2 to the 63rd to negative 2 to the 63rd to positive 2 to the 63rd minus 1. That's the range of values. So it would be this. Negative 2 to the 63rd to positive 2 to the 63rd minus 1. And this is that value minus 1. Just like a signed 8-bit number can store the values between negative 128 and positive 127. So this is negative 2 to the 63rd power to positive 2 to the 63rd minus 1. And if we're doing the unsigned version of this, that is 0 to 2 to the 64th. That's unsigned.
To minus 1.
Yeah, because it's 0 to it. 2 to the 64th is the number of unique values. And then the follow-up question for that was, what? Why are they different? So why is this range, is the number of values, the number of unique values there, different than the number of unique values here?
Exactly the same.
Exact same number of unique values. Just in this case, we had to store negative numbers as well as positive numbers. So I utilized my unique value range to cover numbers that went as far as I possibly could on the negative side without giving up distance on the positive side. Right?
So right in the middle.
So that's 2's complement is how we represent that guy. All right? Now, if we only need to handle, so an unsigned value means only positive numbers, 0 or greater. That means I no longer have to represent numbers on the negative side. So I just start at 0, and now I can go farther on the positive side. So I'm representing the exact same total number of unique values with 64 bits. I just have to decide if I want to account for negative values, I'm going to use 2's complement and give up distance on the positive to gain distance on the negative. Otherwise, I'll just keep everything positive and I get more values, more positive values.
And when you say more values, you say the double of values than the first one, correct?
Well, so here, so we can deal with normal numbers. Let's assume that we're doing negative 2 to the 7th power to 2 to the 7th power minus 1. So this is going to give us negative 128 to positive 127. As opposed to 0 to 2 to the 8th power minus 1, which is 0 to 255.
Okay, so it is 255 divided by 2. Half of them negative, half of them positive.
And then you have 0.
Okay.
Yeah, but we don't have 2 zeros. That's why we have an extra value on the negative side. That's what 2's complement gives us. So this is 256 unique values, right? This is 256 unique values.
How was it decided to put it on the negative side?
Well, they didn't decide to put it on the negative side. That's just how the math of 2's complement works out. Yeah, so somebody didn't just decide, well, do we put the extra one on the negative or the positive side? The way 2's complement works, it shows up on the negative side because of the add 1.
I think you can consider that mine had 2 zeros.
Yours had 2 zeros?
Yeah.
Well, I grade all my exams in binary, so it's either a 0 or a 1. 1 is full credit, 0 is no credit.
Has
So it seems very problematic if you had one question with 2 zeros in it. It is a very, very, very bad binary grade for that question. I was just telling, I've been doing so much work lately in the, it actually worked out that we had the kind of the 2 weeks off in this class because I've fallen a little bit behind on my grading because I usually do all my grading at the pool. And I've been out of the habit of going to the pool because we've been doing all this work in the makerspace. So I got to get caught up on it now. But what made me think of that, the pool thing? Oh, yeah. What mood I'm going to be in when I'm grading these. Well, actually, it's not going to bode well for you guys because the problem is the exams are like the one thing I can't grade in the pool. It's like in a weird format, the Blackboard instructor for the phone. Huh?
So you're gonna be cranky?
Depends when I'm grading it. I guess if it's early in the morning and I came in and the 3D prints came out nice, maybe not. It's late at night and I'm like, oh man. Okay, is that the end of the exam? Because this class hasn't even heard my horror story from my trip.
Let's hear it.
Yeah, well, let me finish the exam, then I'll pause and we'll talk about it.
9, horizontal memory.
We already answered that one, didn't we?
Well,
Horizontal lets you store really, really, really large values, just fewer of them. Okay, and this is actually related to number 10 as well. So what's the point of having composing memory? So composing memory says, hey, you know what? It is cheaper for us to design a memory cell and then duplicate it a zillion times. And then organize those cells in different ways to accomplish different tasks. All right, so I have a single memory cell that lets me store so much stuff. If I need to store more stuff, I'm going to use more memory cells. Now, what is the stuff that I'm going to store? If I want to store, if the more stuff means bigger values, I'm going to organize my memory cells horizontally. If my more stuff means more values, I'm going to organize my memory cells vertically. So vertically organized memory cells let me store more unique values, whereas, well, they don't have to be unique, more values. Well, they would be unique. They're unique buckets. Whereas horizontal allows me to store really, really, really big values. I just don't, by adding more chips, I don't get more unique values to be stored. I just get the capacity to hold larger values. I don't have to use that capacity. I can store the number 1 in a horizontally organized memory bucket that would allow me to store, pick the largest value you can pronounce type thing. All right, that makes sense? So I think, does that answer both of them?
Yeah.
Oh, then the last part is, so we talked about why is it commonly done in memory production? Cost. But then we said, what are the pros and cons of composing memory? Well, the pros is usually we can now produce lower cost, memory, and we have also the option to build memory that kind of is custom made for the kinds of values that we're going to store. So you can make kind of custom solutions for people without creating brand new memory organization or brand new memory primitives. If we think our memory cell is a primitive, a single chip, we don't have to reinvent the chip. We just put them together in a weird way, and that lets us solve interesting problems. But what's the con of composing memory? Well, eventually, as we need more and more and more memory, you can all start only fitting so much stuff. So it's kind of like if you're packing a car for a vacation and the stuff you've put in that car really doesn't fit in that car. You know what I'm saying? you got the stuff hanging out of the windows. You ever see the guy leaving Home Depot just holding the thing on his roof? or he has like the tow rope and is going over the top of thing through both windows. He's just driving, holding on to it. I've never done that before.
I thought you said once like you hold the matrix on top of the car.
Yeah, I've done a whole bunch of stupid stuff.
I said like you said like 4 students in the car and everyone has a hand on the matrix.
Yeah.
Got you?
All because we were too lazy to put and we actually had the ropes. Figured, we just have to go a couple of blocks.
Yeah, you live right there.
It's not that far. It's gonna take us more time to tie it up and untie it than just to get home. Takes more time to get it up off the middle of the street with people honking at you.
And another thing,
Does composing memory affect latency? Could. It could. Heck, we'll record the story. That way, Jordan gets a kick out of it.
Yeah, say hi.
And Alexis. So, so you're asking, would having too many cells start impacting latency? I mean, the answer is yes. Every extra cell will slow down latency a little bit, even though we're talking about the speed of light minus resistance. You do have a longer highway to travel, right? So, if I'm traveling at the speed of light from here to Ani, that's going to happen more quickly than if I was traveling at the speed of light from here to the computer lab down the hall, even if there was zero resistance, right? So yeah, the more chips will be more latency. The question is, at what point would it be measurable?
Yeah.
Yeah, I don't. At what point would it be measurable by a human is the bigger question. Eventually it would be. You're right. So you could claim that to be a con. It's not inaccurate to say that, but I think you would run out of physical space on the chip. I mean, if we just think about if you look inside your computer and you got your little slot to stick the memory, right? That's for replaceable memory. Now they're all soldered or whatever, but just using the split. That's going to limit how big your chip's going to be. And even if they, wired it such that, you have it fit in the slot, but you just had this monstrosity coming off the top of it, with chips on risers and risers and risers, you would just still eventually run out of room inside your laptop or inside of your computer case or whatever. I think you would hit that way before you started having latency issues because of the organization of the memory chips.
Because I remember in the around early 2000, it's the time of the DDR was kind of become whether it's popular or not, and compared with SD-RAM, and at that moment, one of the problems is about latency in the DDR. I don't remember if it's related to composed memory or not.
Yeah.
I remember that.
I kind of recall what you're talking about. That might have been during a time when processors kept getting faster and faster and faster, and bus speeds, the highways between the processors and the memory was getting faster and faster, that it could have been that SD-RAM was starting to become the bottleneck. So maybe less about latency within the chip, but latency.
One thing is, I do remember they claim the latency of the DDR is slower than is a problem compared with SDR. So DDR has a larger capacity potential.
Oh, so it's possible, yeah. I don't know why. I mean, it would have to be the way the DDR is put together, which we're looking at an oversimplified version of composing memory. So I don't know exactly how DDR was put together relative to the SD-RAM before that. It's possible that's related to why the latency was different. I don't know.
Okay.
It would surprise me if that was it. I would think it would have more to do with how the memory was. Well, no, maybe not. I mean, if you think about the vertical memory chart that we had, how that one looked a lot more complicated with all the gates and stuff. It's possible if DDR had to do something special to get you that extra capacity while it's still fitting, that the cost of that might have been increased latency.
There will be more and
more gates, whatever, more stuff it has to go through before it finally finds its home.
Extra bits need to be put into the gate.
So probably it was dealing with the composition of the memory, but more about, I mean, in that case, if you're thinking about DDR versus SD, think about that as the algorithm for composing the memory.
Okay.
So DDR was the way that we put these things together to make it work for either vertical or horizontal. I think you mentioned last class that realistically memory today is composed of both vertically and horizontally organized things. You know, we decide, okay, well, here's the biggest values we realistically need to store, and then we want to store a whole bunch of them. So you're going to have within a single memory both organizations. You're going to have horizontal and vertical combined together. But the idea could be, in order to get us more capacity without running out of physical space on the chip, maybe DDR used a kind of a different algorithm, a different way of hooking those up to get you the same result. But it might have been you had to jump through a couple more hoops, which would then increase latency, make the memory technically slower, even though you gained more total memory. It's possible. Okay, so that's the exam. Questions about that?
How hard will be the final compared with this?
Well, I don't know. It's a whole different subject.
Finals doesn't cover this part?
No, final would be a whole different.
Okay.
Yeah,
Return in.
only the new stuff. Yeah, so I had an interesting trip to Florida. Several of you know that my wife has a phobia of lizards.
Yeah.
So that came from Florida previously as well. So we were in the last night we were in Florida. We were getting ready to leave the apartment. This is my grandma's place. I have one living grandparent. And on our way out the door, my wife always figured that, oh, we're up on the 4th floor. This is fine. The lizards can't climb that high, even though they climb the walls. But we don't see them up that high usually. But a little tiny lizard ran in.
No.
Okay, so she was not happy, right? So we saw the lizard. It went under the couch. We took everything out and killed it. Okay, lizard's dead. If it had just ended there, we probably would have been relatively okay. Now, we travel a lot. My wife is usually pretty detailed about like looking at reviews for hotels and things like that because she's always concerned about bed bugs. So we go out to eat that night, and when we come back, you know, she's already somewhat traumatized from the lizard, right? So we come back, and she's sitting on the bed at my grandma's, and I walk into the room, and she doesn't even notice it. I see it first. She has bugs crawling all over her. Like something out of a horror movie. And they were bed bugs. So I reached down, I grabbed one, and I crushed it in my hand, and it explodes with blood.
Oh.
Because bed bugs are like vampires, so they feed on people. So that was my wife's blood. So at this point, we have a problem.
So when you grabbed one, did she know by that point?
Yeah, she knew, and she like almost couldn't react. She was like so upset that she was frozen, right? So I kill all the bugs that were visible, and then she goes into the bathroom and starts finding more on her. So we got that dealt with, and then we left that place and went to a hotel that we had previously vetted from another trip there. We spent like an hour and a half kind of going through all of our stuff, making sure we didn't transport anything, blah blah blah. In the end, there's already been an exterminator come out to my grandma's and stuff. It looks like it probably came from the restaurant we went to, and we just had a couple that hitchhiked with us, 15, 20, something like that, that maybe were in the booth where we were. Because my grandma's didn't have any there. The exterminator confirmed they were bed bugs because we left some dead ones for him. But she didn't have an infestation, so we were fresh and we were pretty thorough at the time. So we pretty much I think we got them all. But they're hard to get rid of. So my wife was concerned that we didn't want to bring them back home. So when you travel, you almost always pack your favorite clothes. Yeah. So we almost, so all our stuff is well, it's gone now. It was in the dumpster this morning. Yeah, so we came home and, you know, I walked into the house with my CPAP machine and a smile, and that everything else was left in the garage, and we basically sealed everything up in bags the next day and threw it away in the garbage. So there's like a $300 pair of like Bluetooth headphones that are in there, and my shoes gone.
Headphones?
Huh?
You left headphones?
It's over the ear. They have padding. Bugs, those bugs, they have padding on them. They're like, you know, they're over the ear with padding, and that's where they get up. That's like a bed. They get up in there and lay their eggs. That could be 4 zillion bed bugs in the house. Well, you can go find them in the dumpster. They're out there somewhere. And then what was really unfortunate is the very next morning we had the first snow, and I had thrown away my coat. So I don't have, well, I have one now. Amazon, at least they have rush delivery. So I have a coat now. But yes, that was
That's awful.
yeah, it kind of sucked.
Yeah.
But so we were gonna go to Vegas over Thanksgiving, but that we canceled that. Vegas is like the bed bug capital of the world, and you know, before it was like, you know, hey, there's a chance that you might have bed bugs. But, you know, she's pretty thorough with vet stuff, but anything that was a chance before is now a certainty. But we're going to still do our cruise in December as of right now. So in the big scheme of things, you know, if I were actually, you know, for those of you who like met my wife before, I would say she's actually handling it all way better than she probably should be, given like 2 of her major phobias happened within an hour.
Yeah. I would be having a major meltdown.
Yeah. So I don't know. She held it together pretty well. Yeah, I don't know, but it's been a little bit of a stressful 4 or 5 days. I think the worst is over. Although she canceled paint night. We were supposed to go to paint night the other night. Yeah, she didn't want to go.
She's just traumatized.
Yeah, I think that's probably she was on the borderline. She's already gone out to Kohl's to buy new clothes and stuff, so it's not like she's locked in the house or anything. I just think, you know, just still not feeling great post trip, and maybe just didn't really want to go out, and so it's fine. We used the 3D printer. We designed something at the house instead. So I'm artsy fartsy now.
Like an embarrassing dad.
Which part? Artsy fartsy? With saying the fartsy part?
The whole thing.
The whole thing's like an embarrassing dad?
Yeah.
Which part? What's part's embarrassing?
Artsy fartsy. It's just awkward. You come here
Is it?
40-year-old man.
I don't know. My wife likes painting and crap. I think it's stupid. But it's something we do together. You know, so if you've been to my office before and you see I have paintings in there for my our paint nights, she takes me to these paint nights, and you have like a professional artist there who like shows you what you're supposed to paint. They show you like, this is what it is. So you have like the final product, and then they take you through it from scratch. I go off script immediately. So I've done like Pac-Man and an Android logo, and one time I got in trouble one time though. I tried to paint. You can't paint with like barbecue sauce. It doesn't dry like paint.
You'll live and learn.
I know. Tabby yelled at me so bad. She said, "Is that your food?"
That's what might give bad bugs.
You got me.
Well, I didn't have any brown paint, so I needed barbecue sauce.
It's your fault. She comes by and you're like, this is your fault. I ran out of brown.
I didn't run out. I didn't have any to begin with. And then she said, "Oh, I have brown." Well, because the painting we were supposed to be doing did not require brown paint. So that's why there was no brown paint given out. But I was drawing. I have a picture. This was actually one of my favorite ones too, because it's a picture. It's a Jack Daniels bottle with Mr. Gonzalez hugging it, It's off a real photograph. We have a photo of Mr. Gonzalez on a Jack Daniels bottle. But so I needed like the brownish tint of the Jack Daniels, right?
Mhm.
Barbecue sauce seemed perfect. It was not. It just gets sticky. It does not dry.
It's not.
So I had to wait for all the paint to dry so I could wash off the barbecue sauce and then repaint it.
Now you know.
Yeah, now you know. What did your wife think about this brilliant idea of putting barbecue sauce?
Oh, she was mad. She yelled at me. She yelled at me in front of all those people.
I would have loved this.
I would do the same thing.
She's mean sometimes. I think she'd be all happy. I'm sitting there making a fun night of it, right? Like oh, like a Picasso.
Do you have a picture of any of her paintings?
I think from almost every single one of them, we have pictures afterwards of me holding my painting and her holding what's it's supposed to look like.
Really?
Yeah, she's good,
I'd love to see it.
but I mean, not as good as me.
Of course not.
I'm artistic.
So you just go out with
You're
your
artsy.
I'm artsy fartsy.
You bring it that full circle.
That's because he doesn't know how to bring conversation to a close.
Why? Something else happened?
No.
All right, whatever.
Oh my gosh. that's funny.
Okay. Yeah. So that's the story. All right. So questions about any of that junk? All right. So let's at least get started for a few minutes on our. Well, heck, let's take 5 minutes. We'll take 5 minutes and then we'll because we're at 7 right now. It'll mess up our. So come back just like at 7:02.